Hi everyone, I want to use this video to talk to you about some specific discrete random variables that we're going to learn about. So yeah, let me share the notes and get started. Let's see here. So first off, let me say that we're not going to go over the formulas for these. I don't know if I've made the right choice in opting out of the formulas, but I'm just going to have you do it all on your calculator because you're not going to want to calculate this stuff by hand. It's a giant mess, and the formulas are complicated enough that I don't want to spend another, I don't know, half an hour to an hour explaining them. And they're not relevant to you anyway. And they're also not a thing that we're going to be doing a ton of in the class. So I don't really want to spend more of your brain space on that than we have to. If you're interested, though, they are actually pretty neat. I really like how the formulas are devised, but they do take some explaining. So if you're interested, I'll be happy to explain them, but we're not going to worry about them as part of the class. What did I just do? Okay. So there are three different kinds of discrete random variables that we're going to talk about. There's binomial, geometric, and Poisson. And the first two, binomial and geometric, are going to seem very similar at first because they are. They have the same type of events, but they count different things. So both of them use Bernoulli experiments or Bernoulli trials. And so I first want to explain what those are, and then we will talk about geometric or binomial and geometric. So a Bernoulli experiment is a probability experiment that has these three properties here. So you have two outcomes. All the trials are independent, only two outcomes. That's really important. You can't have like three or four. The trials are independent, and the probability stays fixed from trial to trial. So yeah, so those are the requirements. The classic example of this is flipping coins. If you flip a coin, you have the same probability, heads and tails, regardless of what you flipped last time. There's only two outcomes, heads and tails, and the probability of success stays the same the whole time. So that's the way you want to think of Bernoulli. Is you're doing one thing, and you got the same probability of success every single time, and what you did on a previous trial or the outcome of a previous trial has no effect on the future trials. All right, so those are Bernoulli experiments. And if we are counting the number of successes, like if we decide, all right, we're gonna flip the coin 50 times and see how many heads we get, that is binomial. And if we say, all right, I'm gonna flip the coin until I get heads and then count how many times it takes me to do that, that's geometric. And so they're both using Bernoulli experiments, but they're counting different stuff. So let's talk about binomial. So binomial is actually the most important discrete random variable that there is. A lot of stuff that, excuse me, I've clicked badly here. A lot of stuff that we do is actually based on binomial random variables, although you'll see it more later on when we start doing normal. I'll try and explain the connection between them. The normal distribution is an extension of binomial random variables, essentially, roughly. Anyway, they're very important. They're the most important of the discrete random variables. So a few things to notice. I'm going to give you one of these lines in each of the for each of the random variables, and also for the continuous ones that we do in a video or two. And you really want to pay attention to, at the very least, this. You definitely need to know the notation, the shorthand notation for all the random variables. And each of these random variables has its own shorthand notation. And they can be really confusing because they all look very similar. They're like capital letter and then parentheses with some number of things in the parentheses. And so you have to pay close attention to which one you're looking at to know what to do with it. Give you the expected value and the formula for the variance. You should definitely write these down. You get a page of notes on your for your test. You should definitely have these on there because I will ask some of the time, or I will ask for some of these. But you don't necessarily need to know how they're computed. Like, for instance, for me to explain why the variance is NPQ for binomial random variables, we would need to understand factorials, and then we would need to know calculus 2, so I could show you how to integrate things. And like it's just not a it's just a thing to remember, essentially, that we're going to use, but not a thing that you need to know where it is devised from. Although if you do want to know, I'll be happy to show you. They're all pretty interesting, and they're all a little bit complicated. On the other hand, you should probably understand this, that the mean of a binomial random variable is the number of trials times the probability of success. Oh, I should probably explain what these letters are, shouldn't I? N and P, N is the number of trials and P is the probability of success. Probability of success on each trial. And remember, the trials are fixed, or the probability of success is fixed from trial to trial. So this P doesn't change. It's just some number that stays constant throughout the problem. And I hope this makes sense. We've actually used this before, believe it or not. If you think back to the last video where we talked about coin flipping and how many heads we expected to get in 3 flips, we said, well, if we're getting heads half the time and flipping 3 times, that's about 1.5 heads per trial. Well, that's exactly this. We're getting heads half the time, right? That's the probability of success. And we're flipping the coin 3 times. That's the number of trials. We get number of flips times the probability of getting heads, right? Number of heads, or on average. So remember these things. I will refer to them, and then yeah, we'll see how to do all this stuff in the calculator in just a second. So I'm not going to show you the formulas for calculating these, although we could. Like I said, they're a little complicated. They involve factorials and choice functions, and I don't really want to explain those. It's not that I don't want to explain those. I love explaining those. It's that they are hard to comprehend, and if you are not familiar with those things already, it's very easy to get lost in the details, and it makes this harder to understand. So we're going to skip over that and just use the calculator instead, which is fine because that's how you were going to want to do the actual calculations anyway. So I don't think we're losing too much there. So here's the thing. Here's what we're going to be calculating. So let me very briefly sketch you a binomial distribution. So binomial distribution looks something like this. Let me whiteboard this up here. So if we have, let's say we're doing something that's got like, well, let's do 3 trials. So we could get an outcome of 0 or 1 or 2 or 3. This is probability. 0, 1, 2, 3. So we could have, so if we're flipping a coin, we're going to get probability of 1/8 of getting 1 heads. 3/8, or of getting 0 heads, excuse me. 3/8, 1, 2, 3. 3/8 of getting 1 heads. 3/8 of getting 2 heads, and 1/8 of getting 3 heads. And your binomial distributions all look like this peak in the middle and then sloping down on the sides. In fact, the bigger n gets, so in other words, the more trials you do, the more it looks like a bell curve, more it looks like this. And in fact, if you let n go to infinity here, the thing that you get is this. So that's the connection between normal distributions and the binomial distribution, is if n is sufficiently large, this actually looks a lot like this. So you want to think of this as like a bell curve, basically, but discrete and with bars instead of like infinitely thin lines. So that's what your binomial distribution looks like. So what we're going to be finding in the calculator mostly is the probability of certain events. So for instance, if I wanted to find, so again, this is flipping 3 coins. So if I wanted to find the probability of x equaling 2, right? That would be 3 out of 8. I know that one. If I wanted to find the probability that x is less than or equal to 2, that would be, well, I would add up the areas of these bars, essentially. So this is 3/8, 3/8, and 1/8 gives me 7/8. And the way to calculate those numbers for us is going to be on the calculator. I'm just going to show you how to find these things on the calculator. Now, there's 2 different functions that we're going to use on the calculator, one of which is for equals and one of which is for, oh, that's not the equals I meant to circle. It's this one I meant to circle. One of which is for equals and one of which is for less than or equal to. So remember how I said, so for this less than or equal to, what we did was we were going to add up the area of this bar and this bar and this bar and this bar. Well, there's a function in your calculator that does that, that adds up all of those things for you, which is really convenient. Because otherwise it can get really tedious. Like imagine n equals 50, which it's going to in our example here in just a second, and you don't want to add up like 37 bars. That's not fine. So your calculator will do that for you automatically. So we're going to learn how to do that in calculator. So let's go see what we're going to do with these. Mostly we're going to be calculating probabilities. So let's see what that looks like. All right, so there's two, like I said, there's two different functions we're going to use for these called binomial PDF and binomial CDF. And of course, there's going to be a different function for every type of random variable, right? Binomial is for the binomial random variable, obviously. It's the PDF and CDF that we're interested in. And the way you want to think of these, PDF is relative frequency. That is the probability of for just equal to, and then CDF is cumulative relative frequency. That's the one that adds up everything up to a certain number. So let's see what that looks like. Yeah, so in your calculator, this binomial PDF with n, p, and x. So n is the number of trials, p is the probability of success, and x is the number that you are interested in. That changes from problem to problem, right? So n and p are going to be the same for any given setup, but x is going to change depending on what probability you're trying to find, which I'll show you in just a second. Binomial PDF of NPX will give you the product of exactly x successes. Binomial CDF NPX will give you the probability of getting x or fewer. That's the one that adds everything up. So let's see what one of those looks like. All right, so here's our example. LeBron James' career free throw percent is 74%. At least it was when I wrote this worksheet last year. I think he's improved since then, but we'll just go 74%. So for our experiment, he shoots 50 free throws, and we let x be the random variable that counts the number he makes. So notice that this does meet the requirement for a binomial random variable. He's doing something a fixed number of times that has the same probability of success each time, and then we are counting the number of successes. Oh, and each trial is independent of the others. Now, you could argue that maybe there's going to be hot streaks and cold streaks. I'm just going to assume that those don't exist. Statistically, by the way, there have been studies of this, and they generally don't exist. So yeah, so we're just going to assume that those don't exist and each one is independent of the others. He's got a 74% chance of making every one of them, and he's doing he can either make or miss. There's only two outcomes, and he's shooting 50, and we're counting the number of successes. So all the things required for binomial random variable. I noticed that there were a lot of those things, right? You got to meet your Bernoulli experiment. Only two outcomes. Outcomes are independent. Probability of success is fixed. And then the thing that you're doing is you're counting the number of successes in a fixed number of trials, which we're counting the number of makes in 50 trials, right? That's our fixed number of trials. So for us, n is 50, p is 74% or 0.74. You're gonna have to put it in your calculator as 0.74. And then x depends on what we're trying to find, right? So for when we're looking for the probability that x equals 35, x is gonna be 35. When we're looking for the probability that x is less than 40, for instance, well, we'll see, but x is going to be 39 there. All right, so let's see how that looks. So we want to find probability that x equals 35. So let's go to a whiteboard and get the calculator open. So I'm going to pop up the whiteboard, clear all this off. So I'm looking for probability that x equals 35. That is to say that he makes exactly 35 free throws in 50 attempts. So the way we're going to find that is I'm going to go to the calculator, which I should have open here. Yep, there it is. Here's the calculator. And I'm going to go to distributions, which is the second function of variables. So I'm going to go second vars. And we're actually going to use almost everything in here at some point this semester. Maybe not normal PDF, or there's a couple of these that we won't use. But we're using binomial, it's binom instead of binomial, whatever, binom PDF, right? Because I want to find the probability that x equals exactly 35. If I wanted to do less than 35 or less than or equal to 35, I would do CDF, and that's, I believe, the next example. So for PDF, this is NP and X. If you don't have this screen right here on your TI, trials is N, P is P. And then the X value is X, obviously. I think those are fairly straightforward. So we got 50 trials. Oop, number lock's not on. 50 trials. His probability of success is 0.74. You got to enter it as a decimal, no 74. And then the X value, that's the number that we're interested in finding the probability of him making, is exactly 35. So paste that in. And if you don't get that screen, you just type this into your calculator. You'll have Binomial PDF, and then it'll put a parenthesis. And you just literally type in 50, 0.74, 35, close parenthesis. Enter. So almost exactly a 10% chance of making exactly 35 free throws in 50 attempts. So let's let me pop back over to here, whiteboard, where I can say that this is Binomial PDF of 50, 0.74, X was 35. Excuse me, stuff's in the way here. And that is about equal to 0.10. Okay, great. That's how we're going to use the calculator to find binomial probability, is by using binomial PDF and CDF. So let's see what the next question is. All right, we want to find the probability that X is less than or equal to 35. Now remember, CDF does less than or equal to. So when I'm going to do exactly the same thing, exactly the same inputs, except I'm going to use CDF, and it's going to not just calculate the probability of making 35, but also the probability of making 34, and the probability of making 33, and the probability of making 32, all the way down to the probability of making 0, and it's going to add all those things up and give it to us. So as you can see, you don't want to do that by hand, right? Because you'd have to do PDF for every single one of them, and that's just a pain in the neck. So that's why we're using the calculator for this stuff, because it is just easier. So, actually, let me go here. Oop, come on. Let me go to the whiteboard and write this down. So we're going to do probability that X is less than or equal to 35 is binomial CDF of 50, 0.74, 35, and we're going to see what that's equal to. It's definitely going to be bigger, right? Because it includes this one up here, but also all the ones less than it being added to it. So let's see what that answer comes out to be. Let's go to the calculator. We're going to go to distributions. So second vars, binomial CDF. And by the way, I don't know if you know this, but if you hit up at the top, it'll scroll to the bottom, like Pac-Man style. Binomial CDF. 50 trials, 74% chance of success. 35 is the number I'm interested in. And here we get 30.75%, 0.3075. All right, let's go put that on the board. 0.3075. Okay. So let's see what other kinds of questions we can ask, because that's not all of them, right? We could find the probability that X is greater than 35. Now, you might ask yourself, well, if there's no function in the calculator for greater than, right? There's PDF for equal to, CDF for less than or equal to. How do you do greater than? Well, the way you do greater than is the complement rule. Remember, I said this thing was going to come in really handy, but I said this a while ago when we were doing probability. So let me go to the whiteboard and draw some stuff here. So if I put the number of free throws that LeBron makes, so 0 up to 34, 35, 36, 37, up to 50. All right, I hope you'll agree that is an exhaustive list of the number of free throws that you could make in 50 tries. And I want to know, what's the probability of making more than 35? I didn't leave myself my room here, but making more than 35. Well, what I want to do here is I want to circle all of the outcomes that I am interested in. So these guys are in this box, right? Those are the ones that I'm looking for. Well, you might notice that if I add up the probabilities of all of these, since he's got to make some number of free throws between 0 and 50, right? The total probability is 1. So that means if I want the probability of this blue stuff, I can do 1 minus the probability of the stuff that I don't want, which is this. So that's what I'm going to do. I'm going to do 1 minus binomial CDF of 35. So 1 is the whole thing. So let me get this on here. So hello, there we go. Total probability equals 1. So probability that x is greater than 35 equals 1 minus, well, let me do this differently. Let me say that the probability that x is greater than 35 plus the probability that x is less than or equal to 35 equals 1. So therefore, that's the symbol for therefore, by the way, in case you didn't know that. Probability that x is greater than 35 is 1 minus the probability that x is less than or equal to 35. Right? Which makes perfect sense if you just visualize it, right? If all these add up to 1 and I'm looking for this, well, then I just do 1 minus the stuff I don't want. That's how you do it. And so that's literally what I'm going to do. I'm going to do 1 minus binomial CDF of this previous thing, which, I mean, we already know what it is, so we can actually just write down the answer. But that's what, like, if I didn't already know this, I would do 1 minus that. So that's the way I'm going to do this. And by the way, this technique of writing down everything and boxing the things that you want is a thing that I'm going to do a lot, and you should absolutely do as well. It's really, really convenient to make sure that you're putting in the right numbers into your calculator. In fact, it's actually fairly hard to do this without it at first. I know that sounds really strange, right? Writing down a list of numbers is going to help me. It will, I promise. It really does work. If you're already good enough at it and you're already totally happy with your ability to know exactly what numbers to put in, maybe you don't need it. I still use it, to be honest, even though I've done this quite a lot. So let me clear off all this stuff. I'm going to select all this so I can delete it. Get everything? Yes. Okay. Oops. Now I have to it up again. Hang on. Sorry. All right. So I want to find the probability that x is greater than 35 equals 1 minus the probability that x is less than or equal to 35 equals 1 minus 0.3075, which is, and again, I'm going to use that trick of subtracting from 1. Remember, notice I said that, or if you remember, I said that's a thing that comes up surprisingly often, and it does. So I want to total up to 9, 9, 9, and 10. So I'm going to go 6, 9, 2, 5. There we go. So that's my probability of that. Let's see what else we can ask. We can do some other interesting stuff with this. We can find the probability that x is between 30 and 40. This one's going to take some thinking because, again, there's no function for between. So what we're going to do is we're going to go identify the pieces that we want, and then chop out the stuff that we don't want. Like that's going to be the usual strategy that we're going to employ for these. So go back to the whiteboard. So between 30 and 40, not including either one. All right. All right, so I want to find the probability that, oh, that's not the right thing, 30 less than x is less than 40. Okay, so I'm going to do the same thing I did before there. So we're going to go 0, let's see, 28, 29, 30, 31, 39, 40, 41, 50. Okay, so the ones that I want here, I'm going to circle in blue. So the ones that I want are the things that are bigger than 30, so 31, and smaller than 40, so 39, right? So I want this stuff here. That's the good stuff that I want. So the question is then, how do I isolate that stuff using just CDFs? And you could do, if you wanted to, you could do PDF of 31 plus PDF of 32 plus PDF of 33 up through 39. And that would work. And actually wouldn't be that bad. There's only 9 of them, right? Like that doesn't take eternity to do. It's a little tedious though, and we can do better. So what I'm going to do is I'm going to do CDF of 39, because that's going to get this stuff and less, right? And that includes all the stuff I want, but also a bunch of stuff that I don't. And then I'm going to subtract off the stuff that I don't want. Right, so what I'm going to do is CDF of 39 binomial CDF of 39, and that'll give me 0 through 39 added up, and then I'm going to subtract off CDF of 30 because that'll get rid of 30 and below. Right, so that's going to be my strategy here. So let's go ahead and do that. So this is going to be binomial CDF, and I'm not going to have room on one line here, of 50, 0.74, 39, minus binomial CDF 50, 0.74, 30. That's the thing that I want. So I'm going to do all the stuff. I'm going to get all the stuff that I do want, right? 39 and below. That also includes a bunch of junk that I don't. And so I'm going to subtract that off. So that's my strategy. Let's go do it. So I'm going to do binomial CDF of 39. Now, here's an interesting thing. It doesn't automatically calculate it for you. It takes that as an entry in your calc, or as an entry in the calculations that are blue. So I'm just going to do that minus, that's times, that's not the right button, minus binomial CDF of 30, as we figured out. And notice that it would actually be relatively hard to figure out that I don't want to include 40, but I do want to include 30 just by looking at the problem statement. This is why I really recommend writing out all the different outcomes and circling the ones you want. It makes it really clear in your mind which ones to include and which ones not to include, or at least it should. Excuse me. So let's paste that in. So now I've got binomial CDF of 39 minus binomial CDF of 30, and I get 0.7659. Let's go write that down. Hello. There we go. Go ahead and delete this stuff. Pardon me. Eraser. Zoom eraser is neat. Does a good job of getting stuff. So this 7659, I think, is about equal to 0.7659. So it's about a 77-ish% chance that he'll make between 30 and 40 free throws in 50 tries, which is about what you'd expect, right? It's very likely that he's going to be around his average, which his average is 74%, and so his expected value would be 0.74 times 50, which is 37. So you'd expect him to make 37 free throws, and then if not, then he's probably going to be around there somewhere, right? He's probably not going to only make 20 out of 50 free throws. He's a better shooter than. He's probably not going to make 49 out of 50 free throws because he's not Steph Curry, right? So, yeah. So let's go look at this. There we go. Now, in F, I have specifically worded this in a confusing manner because this is a very specific confusing manner that problems in statistics are often worded in. So I want to find the probability that the number of free throws he makes in 50 attempts differs from 35 by at least 5. So in other words, by 5 or more. So when I say differs from, I mean, is that far away from? So things that differ from 35 by 5, by exactly 5, are 30 and 40, right? 30 is different from 35 by a distance of 5, and 40 is also different from 35 by a distance of 5. If I say that it differs from 35 by at least 5, what I mean is the number of free throws that he makes in 50 tries is 5 or more away from 35. So 30 or less, or 40 or more, right? So let's go back to the whiteboard. I'm going to erase the other things on the whiteboard there and see if we can figure out how to write this. So I'm going to erase all this because I'm running out of room here. So we've got 35 here. So what do I do? Third, 29. I guess I got to write a lot of writing here. 30, 31, 32, 3, 34, 35. Oh, I didn't leave myself enough room. Maybe I did. Maybe that's good enough. Okay. So things that differ from 35 by exactly 5 are 30, 30, and 40. And so if I am differing from 35 by at least 5, then I want all of this stuff and all of that stuff. Right? And of course, this goes down to 0, that goes up to 50. I just didn't write them. And so we can find this stuff. Now, we can certainly do the thing that we just did a second ago, 1 minus it, right? We found the probability of getting 31 through 39 was like 77% or 76.5% or whatever it was. And so this is the complement of that. We could do 1 minus that and get our answer, but let's pretend that we didn't see that, all right, that we hadn't just done that problem. The way I would want to do this, I would say that probability that x is less than or equal to 30 or x is greater than or equal to 40 equals. So what I could do is I could do this guy. So we're not going to be able to do this all in one piece. It's literally 2 pieces, right? So we're going to have to find this and this separately. So if I wanted to find this, I would do CDF of 30. And if I wanted to find this, I would do 1 minus CDF of 39. Right? So CDF of 30 will give me all of these things. 1 is all of them. And so if I just want 40 to 50, I would subtract off the stuff and the stuff that I don't want that's less. So 39. So CDF of 39. So I can write this as binomial. I'm not going to write the stuff in the middle, or not the numbers here. Binomial CDF. No, I guess I am fine. 50. 0.75. I mean, I might as well, right? And 30 plus 1 minus binomial CDF of 39. 50, 0.74, 39. Right, so this bit right here, this first one is the first blue box, and the second bit is the second blue box. Now, you might notice that I said we could just use the complement rule and do 1 minus that thing we just did, which we totally can, right? And it actually is the same thing. Because what we did in the previous part was we did CDF of 39 minus CDF of 30, right? So we did, so we could do 1 minus that. So we could do 1 minus binomial CDF of 39. So 50, 0.74, 39 minus binomial CDF 50, 0.74, 30. Right, we could do that, and if we do, notice what happens. I distribute this minus sign, and I end up with 1 minus this plus, from the minus a minus, this, which is exactly the same thing as this thing up here. It's 1 minus CDF of 39 plus CDF of 30, right? So it's exactly the same either way you do it. I've had students ask, well, wouldn't one be easier? They're entirely identical. Whichever way you want to do it, it really makes no difference. Now, we have a nice convenient previous part where we know what this bit inside is. So it was 0.7659. 7659, yeah, 0.7659. So if I want to do 1 minus that, I can just do 1 minus. And by the way, here's a little trick for you, not a trick, but a calculator button that not everybody knows about. There is answer right here. It's the second function of the negative sign. And so if I do second this, it will do 1 minus whatever the previous line was, which will be the thing we said. Now we could do this again, we could do this quickly in our heads by knowing I want, let's say I'm going to 4 decimal places, I'm calling it 7, 6, 5, 9. I would want this to be 9, 9, 9, 10. So it's going to be 2, 3, 5, or 2, 3, 4, 1. Right, so 0.2341. So that is the probability that he makes a number of free throws that differs from 35 by 5 or more. Right, very complicated way of saying that, but actually a very common thing to do in statistics a little bit later on. There's lots of times where we're going to be interested in the edges of a distribution and how much area is in them. So this is the sort of thing we actually end up calculating quite a bit. Okay, so that is binomial random variables, and we're going to learn about 2 other kinds of random variables. And you might say to yourself, oh my God, that's going to take forever. It's not going to take forever because the hard part was the CDF and PDF stuff. I'm just going to explain when to use them and then show you a couple of examples of using them. And the CDF and PDF stuff is going to be exactly the same. So let's go look at that. Back to the notes. Here's the notes. Okay. So geometric random variables are very similar to binomial random variables. They use Bernoulli trials, you're just counting something different. So instead of counting the number of successes in a fixed number of trials, you just count the number of trials until the first success. So in other words, whenever something happening for the first time ends the experiment, that's geometric that you want. And you're interested in how many tries it takes, then you want geometric. So that's what we're going to use. Here's the notation. Your book uses this G of P, where P is probability of success. And then here's the mean and variance and standard deviation of those things. Again, write them down. You don't necessarily have to know where they come from. Explaining where even the mean of this comes from is relatively complicated. It takes a little bit of math. But it's 1 over P. 1 over probability of success. So N and P mean the same thing, but there actually isn't an N in this with geometric random variables because there's no fixed number of trials. In fact, the theoretical number of trials is there's no upper bound to it. You could just keep not getting the thing to happen. So for instance, if I wanted to stop flipping coins when I flip a head, I could just keep flipping tails forever, like theoretically, right? In practical terms, of course, that's not actually going to happen. But in theory, there's no upper limit to the number of trials that it might take me. They use Geom or possibly Geomet PDF. I don't remember, but the PDF and CDF are the same thing. They use P and X, right? No N, but everything else is the same. So we're going to use these when we are counting things, when we are counting the number of trials until the first success. So until the thing happens for the first time, and then the experiment ends right there. All right, so an example of that is something like this. Janet is buying a used car. She's going to test drive cars until she is happy with one and then buy it. There's no need for her to go keep going afterwards, right? We're not interested in if she test drives 45 cars, what's the probability that she buys 7 of them? She's going to buy 1 car and then stop the experiment. So there's a 40% chance that she is happy with any given car, and we want to let X be the random variable that counts the number of cars that she test drives until she finds one that she's happy with. So minimum value of 1. It's not possible to get 0 because you can't have a trial you can't have a success in 0 trials. You got to have at least 1 trial. So we want to find the following. Number of cars she should expect to test drive until she finds one that she's happy with. Well, that is the expected value. So again, this might be the first time. When you see the word expect, you should think to yourself, aha, that is asking for expected value. Even though when we do this, we're going to do 1 over 40% because that's what the formula is, 1 over P. That's not an integer, but that's still the thing that the problem is asking for. So switch over here. That's the whiteboard. That's not what I meant. I meant to go to here. So we're just going to do 1 over 0.4, right? So 1 over P, we get 2.5. So on average, if Janet did this experiment many times, she would expect that if she averaged the number of trials that it took her, or the number of test drives that it took her to find a car that she is happy with, that the number that she would get would be 2.5. She's not actually literally expecting to test drive 2.5 cars, because that doesn't make any sense, right? 2 or 3 is probably the way you would put that in plain English. So She's expected. So the expected value is 2.5. Let's see how to calculate the other thing. So let's go back to the notes and see what the other questions were. Okay, so we want to find the probability that x equals 2. So the probability that it takes her exactly 2 test drives. So in other words, you only get a second test drive if the first one fails. So it's the probability that the first one is that she doesn't like, and the second one she does. Right. So that's what geometric CDF, or excuse me, that's going to give me. I'll use Geomet PDF for that, or Geom PDF, whatever they call it. Geometric PDF to find that one. This one for less than or equal to, again, CDF specifically calculates less than or equal to. So this is going to be geometric CDF of 5. And then this one is going to be 1 minus geometric CDF of 5 because it's the complement of that one. So let's go to the whiteboard, write these things down. Probability, first we get rid of this, clear everything. So we're going to do 1 minus, or probability that x equals 2 is going to be geom PDF, because it's equal to, of p, which is 0.4. That's the probability of success, and then x is 2. Let's go see what the calculator says that is. So you find this in the exact same location as the other PDFs and CDFs, including the one we just used. So distributions, they do call it Geomet. Sorry, I never remember what the calculator calls things. So Geomet PDF, probability of success is 0.4. X value is 2. Paste. 24%. There's a 24% chance. I wrote it as actually equal to, or it's approximately equal to, when what I meant was exactly equal to 24%. All right. The other ones were probability that x is less than or equal to 5. So here, because it's not just equal to, it's less than or equal to, I'm going to use geometric CDF. Right. So I'm going to do geom CDF of 0.4 and 5. And let's see what we get for that. Calculator. So same place, distributions, geometric CDF, probability of success 0.4, x value is 5 this time, 0.92224. I might as well write all 5 of those places. I usually only go 4 decimal places, but if there's only one more, I don't see why not. Why not? So this is 0.92224. So there is a 92.224% chance that it will take her 5 or fewer test drives. So it could be 1, 2, or 3, or 4, or 5 test drives. All of those are included in this. All right, so the probability that x is greater than 5, well, that is pretty clearly the complement of this thing, right? So this is 1 minus 0.92224, which again, we can do quickly in our heads by knowing that I want to add up to 9, 9, 9, 9, and 10. So it's going to be 0.7776. 0.07776. So about a 7.8% chance that it takes her more than 5 tries, or more than 5 test drives. There you go. That's geometric. I think that's all I really want to say about geometric. You just use it in a different situation. It's got very similar setup. You're just counting something different, or very similar setup to binomial. You're just counting something different. You're counting number of successes until number of trials until the first success, which then ends the experiment. Poisson is entirely different. Poisson is going to seem very vaguely defined, and it kind of is, I got to be honest. And the reason it's so vaguely defined is that it is applicable in many, many situations, as it turns out, which we will see a little bit after we do chapter 5, continuous random variables. We will see that it is related to the exponential distribution, which is a continuous random variable, in an interesting way. You can go ahead and read this in your book if you want. Check out the end of chapter 5 and they explain it. So Poisson random variables do not use Bernoulli trials. Poisson random variables count the number of successes, or the number of instances of something occurring in a fixed time and or space. And yes, I understand that that's very, 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 very vague. in general, there is, well, there is, but we'll talk about it later. But there isn't a clear definition just from looking at a problem of when you should use Poisson random variables. In fact, it's so unclear that Poisson, the guy who found this distribution, never saw it used in his lifetime. It was only used years after he was dead. In fact, the very first time that Poisson random variable, or that a Poisson distribution was used to model something, as far as I know, is a Prussian army quartermaster, he's Polish, I believe, named Władysław Bortkiewicz. I'm sure I'm saying that name wrong, but it's something like that. He was a quartermaster in the Prussian army in the, I want to say late 9th or early 19th century, maybe late 18th, probably early 19th century. And he was investigating how many people, how many Prussian soldiers died by getting accidentally kicked by their own horses every year, right? There were thousands, like the Prussian army was huge at the time, thousands and thousands of horses. And there's just accidents that happen sometimes, and they would lose a few soldiers a year to this. And so he was investigating it. He just wrote it down. You know, we lost this many soldiers this year, this many soldiers that year, etc. And for some reason, this Prussian army quartermaster was familiar with the work of Poisson. Don't ask me why. And he just noticed that the distribution of people killed every year by accidental horse kick, or Prussian soldiers killed every year by accidental horse kick, just happened to fit essentially perfectly with the Poisson distribution. Seems like an incredible coincidence to me, and it basically was. This is something like 50 years after Poisson died. Like, Poisson had not been around for quite some time at this point. And this was the first recorded instance of anybody ever using his distribution. Poisson, by the way, was not a statistician. He was a mathematician who just happened to notice. He just found this thing that was like, hey, here's this neat distribution. It uses exponential, uses e to the power of stuff that just so happens to all add up to 1. And we can talk about what the requirements for a probability distribution at some point. We will. But yeah, it was just a curiosity that he found and sort of threw out there to everybody and then never used. And then Władysław Bortkiewicz did for the first time many years later. So anyway, back to maybe the point of this. Poisson random variables count the number of instances of something in a specific place and or time. And you figure out if something follows a Poisson distribution, essentially empirically by experimentation, or by its relationship with exponential random variables, which again we'll talk about later. But in general, if I give you a question on a test about a Poisson random variable, I will say the following thing follows a Poisson distribution, right? You're not going to have to guess. I'll just straight out say it, or else not, or else we're using something else. So, a couple of examples here. Number of shark attacks along the Florida coast during summer. Number of spiders in a square meter of meadow at a particular time. Number of industrial accidents in a year at a particular factory. It turns out they all follow Poisson distributions. And in fact, lots of things follow Poisson distributions, which is kind of interesting. For such a weird, vaguely defined thing, it turns out that lots of stuff actually follows these distributions. And so the thing that we need in order to calculate this is lambda. This is a Greek lowercase l. So that's a lambda, and it is the thing that everybody uses for the parameter here. But the parameter is actually mu. It's actually the mean number of occurrences in the fixed time. So mu and lambda are the same thing. It's just a different letter that gets used with Poisson distributions. I don't know why somebody decided to call it lambda instead of mu, but they did, and it stuck, and so now we do it forever. So that's the thing that you need. That's the parameter you need, is the mean number of occurrences in whatever fixed time you're talking about. Time or space that we're talking about. So let's see what that looks like. Poisson PDF and CDF, same deal. The X means the same thing, right? So there's your parameter, and then there's the number you're interested in. Yeah, so let's see what this looks like. So there are an average of 82 shark attacks worldwide in any given year. I believe that's actually true, by the way. I looked this up a couple years ago, and that's about how many there are, which might seem like a lot of shark attacks, but it's a whole year and the whole world, right? And so that actually seems like a very small number to me. When I say shark attacks, I mean sharks attacking humans. Obviously, sharks attack other things like dolphins or fish all the time, but this is the number of sharks attacking humans worldwide in any given year. And it turns out, and this is also true, that those really are modeled well by a Poisson distribution. So I'm going to let X be the number of shark attacks on a given day. So notice I changed the time frame here, right? So there's 82 per year. So the average number per day is just 82 over 365. Right? So I can say that, let's go to the whiteboard here. Let's erase all this stuff. Clear all the drawings. All right, so I can say that mu of X, which is equal to lambda, is 82 over 365. And so this is the lambda that we're going to use as our parameter throughout the rest of the problem. So let's see, I forgot to check what the other things were. So I want to find the probability that X equals 0. So remember, this is, like, let's put this in words and say that this is the probability that there are exactly 0 shark attacks on some given day, right? So pick a random day, probability that we get exactly 0 shark attacks is going to be Poisson PDF of 82 over 365, comma 0. And the others are less than or equal to and greater than 2. Okay. So probability that X equals 0 equals Poisson PDF of 82 over 365, comma 0. And of course, the calculator will do that. So let's go do that on the calculator. Calculator. All right, so we're going to go to distribution. So same place. It's all in the same place here. So Poisson PDF of 82. And now they call it mu here. I don't know why. Your calculator used to call this lambda. And if you have a physical calculator and are not using this one on the computer, I bet yours still does. Mu is the more sensible letter to use for this. Mathematicians and statisticians don't use that, though, in general. They typically use lambda. So they mean the same thing. Just, sorry, the calculator is a little inconsistent. 82 over 365. And the X value is 0. It's PDF, yeah, there we go. So we got 0.79888, which seems like a large probability of getting 0 shark attacks until you think of it, until you realize there's only 82 in a whole year, right? And so that means that most days don't have any shark attacks. Most days in the world, most days there are no sharks attacking humans anywhere in the world. It's kind of neat. Yeah, and so apparently on 79.88% of days, that's what happens. No shark attacks. So let's go write that down. So 0.7988. And then we're going to do probability that X is less than or equal to 2. So there are 2 or fewer shark attacks. As you can imagine, this is going to be a really large number, right? 80% of the time, there's no shark attacks at all. And then this is also going to include the times where there's 1 shark attack or 2 shark attacks, but not 3 or above. So this is going to be Poisson CDF. Of 82 out of 365, comma 2. And I'm expecting a big number, something well into the 90%. Let's go see what it actually is. So we're going to do distributions, Poisson CDF, 82 over 365, X value of 2. Paste it up, 99.84%. So it's very, very, very rare to get more than 2 shark attacks in a day. 0.16%. All right, let's go write this down. That was the wrong thing. Let's try that again. That's the one I want. 0.9984. So if I'm looking for the probability that x is greater than 2, well, that's going to be the same thing. That's 1 minus 0. When I say same thing, I mean the complement. So totally the opposite thing of the previous one. So this is, and again, I'm going to do this quickly in my head by knowing I want to add up to 9, 9, 9, 10. So it's going to be 0, 0, 1, 6. 0.0016. Right, is the probability of 2 or more than 2 shark attacks in a single day somewhere in the world, right? So very rare, very, very rare. 16 times in 10,000, or about 1 time in 200 or something like that. No, 1 time in 500. That's what I'm trying to say. Anyway, I believe that is all I want to say about random variables. Let's go quickly back to the notes and make sure I didn't miss anything. Yes, that is it. That is all I wanted to do. So make sure that when you're doing this, so a couple tips. Number 1, probability of everything added up is 1. Therefore, if you want to find the probability of, you can use the complement rule really easily, and sometimes it's really helpful. Sometimes if you're doing this on the calculator, it's even necessary, like if you don't have the formula handy. I feel like there was something else I wanted to say. And then we've got 3 kinds of discrete random variables. We had binomial, geometric, and Poisson. Binomial counts number of successes in a fixed number of Bernoulli trials. Geometric counts the number of trials to get the number of Bernoulli trials to get the first success. And Poisson, entirely unrelated to the other 2, counts the number of instances of a certain thing happening in a fixed time and or space, and is basically determined by experimentation whether something is follows an exponential distribution, which is why it took follows a Poisson distribution, which is why it took so long to come up in history. And with that said, I think I am going to go ahead and end the video here. Let's stop that share, and I will see you guys in the next one.